Hey there, and welcome. Today, we're going to get into something really cool, the absolute bedrock of all engineering. These are the fundamental principles that, well, literally let us build our entire world. So let's just dive right in.
You ever just look at a massive skyscraper, scraping the clouds, or a rocket blasting off into space and just wonder, what's holding all that together? What are the invisible rules that make it all work? Well, the answer is actually pretty elegant. It comes down to three foundational ideas: Newton's laws of motion, and we're about to see how engineers use them every single day.
All right, so let's start with the first law. Now, I like to think of this less as a dry scientific rule and more like a personality trait that every single object in the universe shares. And that trait is a deep, fundamental stubbornness.
So what this is really saying is that things just like to keep doing whatever they're already doing. Simple as that. If something is sitting still, it wants to stay still. If it's moving, it wants to keep moving in the exact same direction at the exact same speed. Nothing changes without an outside push or a pull. And this resistance, this stubbornness, it actually has a name. It's called inertia. And it's just an inherent part of all matter. It's not something an object does. It's truly part of what an object is. This is a brilliant way to see the two sides of inertia. Okay, picture a giant boulder just sitting in a field. It takes a massive amount of effort to get that thing rolling, right? That's its inertia resisting the change from being at rest. But once you do get it rolling down a hill, it takes an equally massive effort to stop it. That's the exact same inertia, but now it's resisting the change from being in motion. So why does this matter for, say, an engineer? Well, think about it. A skyscraper's greatest weapon against a powerful wind is its own enormous mass. Its sheer weight gives it so much inertia that it basically just refuses to be pushed around. The building's stubborn desire to stay put is literally what keeps it standing tall.
Okay, so if everything is so stubborn, how do we get anything to move at all? That is a great question, and it brings us right to the second law. This one is all about the relationship between a push, how heavy something is, and the change that happens. It's the rule that explains how we actually overcome all that inertia. Let's just put this in really simple terms. If you want to change how something is moving, you want to accelerate it, you have to apply a force. And this is something we all intuitively know, right? You push something harder, it moves faster. And if the object is heavier, well, you've got to push a whole lot harder to get the same result.
So here's the cause and effect chain, plain and simple. You start with an object and it has a certain amount of mass, that's basically its inertia. Then you come along and apply a force to it. The result, you get acceleration, a change in its state of motion. This little chain of events is, absolutely foundational to engineering. Think about pushing a shopping cart at the grocery store. We've all done this. An empty cart, it's a piece of cake. A tiny little push sends it flying down the aisle. Its low mass means it has low inertia, so it doesn't fight that change very hard. But a cart that's packed full of heavy groceries, yeah, that same push barely gets it to budge. Its high mass really resists that acceleration. Now let's take this idea to a much more extreme scenario, an earthquake. The ground suddenly, violently accelerates sideways. But the building, because of its huge inertia, wants to stay exactly where it is. That difference, the ground zipping back and forth while the building tries to stay put, it creates these incredible forces inside the structure itself. The second law is what tells engineers exactly how strong they have to build that structure to survive that intense internal struggle. This brings us to our third and final law, which I think reveals a really profound truth about how the universe works. And it's this: forces never ever act alone. They aren't monologues where one thing just acts on another. No, they are always a conversation, a two-way street. Now, this is probably the most famous of Newton's laws, but it's also probably the most misunderstood. The absolute key here is that forces always, and I mean always, come in pairs. You can't have a push without something simultaneously pushing back. So wait a second. If the forces are equal and opposite, how does anything ever move? Here's the secret. The two forces are acting on different things. So when you walk, your foot pushes backward on the entire planet Earth. Seriously, that's the action. And in return, the Earth pushes forward on just your foot. That's the reaction. And since you're a whole lot easier to move than the entire planet, you're the one that accelerates forward. In engineering, this concept is absolutely critical for understanding what's called the load path, which is just the journey a force takes through a structure. Every single connection is one of these conversations. A beam pushes down on a column, and the column pushes right back up on the beam.
The column then pushes down on the foundation, and the foundation pushes back. It's this perfect, unbreakable chain of action-reaction pairs that safely carries the weight of a building all the way down into the ground. So, when you get right down to it, these laws aren't just three separate ideas you learn. They work together in this beautiful, intricate concert. And engineers have to be thinking about all three of them all the time to design anything that's going to be safe and stable.
Let's use a bridge to see how this all comes together. So, according to the first law, a bridge that's just standing there is in a state of equilibrium. All the forces acting on it. You got gravity pulling down, the big piers pushing up, they're all perfectly balanced out. The bridge is simply maintaining its state of rest. It's being stubborn. So where do those balanced forces come from? The third law shows us that hidden conversation happening inside the bridge. The heavy weight of the road pushes down on the piers. That's the action. And the piers push up on the road with an exactly equal force. That's the reaction. It's that perfect pairing that creates the balance the first law talks about.
But then, what happens when a big, heavy truck drives onto the bridge? Suddenly, that perfect equilibrium from the first law is disturbed by a new force. And this is where the second law jumps in. It lets engineers calculate exactly how the bridge is going to react, how it will accelerate, just a tiny, tiny bit downwards, a small, controlled deflection in response to the truck's mass. They design it so that this change is completely controlled and totally safe.
See how they all connect? It really just boils down to this. The first law tells us what an object wants to do by default. The second law gives us the exact cause and effect rules for changing that state. And the third law? It tells us where all those forces that cause the changes actually come from in the first place. And that's really the big takeaway here. These laws, they're not just abstract physics concepts you memorize for a test. They are the non-negotiable rules of our reality. For an engineer, these are the very tools they use to shape our world, making sure the buildings and bridges we rely on every day are safe, strong, and built to last. It's pretty amazing, isn't it?